The AMS itself, an accelerator mass spectrometer, has really three components. One is called the low energy end. Let's take the example of carbon. And radiocarbon is present in the environment at 1 million millionths of an atom. So it's a very, very trace isotope. So what we do is we take any sample, we convert it to graphite. There's like a little aluminum button with the graphite in the center of it, and we can mount up to 200 of these graphite targets into a cartridge type, we call an ion source. Because what we're going to do is take the atoms of carbon in that graphite and convert them to ions. We're going to ionize them. Once you get things ionized, you can move them because we use electrical fields and voltage fields, voltage gradients, magnetic fields to move these ions around. So we're going to create an ion beam. So it's a beam of carbon racing out of our source. We bend that beam around with magnets and electrostatic devices and aim it into a big tank. So we're looking at a tank right here. It's a T-shaped tank filled with an insulant, sulfur hexafluoride, because we're going to create a huge voltage in that tank. And so it's like a big transformer that you see in hydro systems, except ours is 3 million volts. So we're going to race those ions towards that positive pole, and then we're going to switch them. We're going to strip those electrons off carbon and turn it to a positive ion just as it hits that positive pole. And it's going to shoot them out the other end. Now we're going up to a few percent of the speed of light. So our ion beam is really rocketing. As we're walking over here now to the west side of the machine, we're at the high energy end. So our ion beam is racing out as the flight path goes into a magnet. And we've got a few control centers along it. These are electronic lenses, so we can change the shape of that beam. So now we're looking at a magnet. It's actually the big, what we call the analyzer magnet. It's 18 tons at whack of energy, because we have to bend that beam at 90 degrees. And so we've got just pure carbon coming down there, but carbon has these isotopes, carbon-12, and then carbon-13 with an extra neutron, and carbon-14 with an extra 2 neutrons. And that's the guy we're looking for. So as we bend that beam, the lighter isotope, carbon-12, bends the most, carbon-13 likewise, but carbon-14 continues on, straight on down that pipe. So we're going to now count, we're going to measure the strength of the carbon-12 and the carbon-13 beams. But carbon-14 is a very weak beam, and we can't measure its strength with current. We have to actually count the atoms of carbon in that beam. So at the very end, we have a detector filled with a gas, isobutane, and the carbon-14 atoms come down and collide with those with the isobutane, and they give off their energy. So this is a high-speed collision. All that energy is dissipated, and each time there's a collision, we measure that energy. So now we come up with a count, and the number of carbon atoms is compared to the carbon-12 that we measured, and that tells us the concentration.